Hello, meteorology students. This is the second half of our forecasting lecture. Today we'll be going over forecasting methods, some models and how we actually use them, forecasting processes, and forecasting maps, because that's what the models actually output to us, and so that's kind of how we analyze the data. All right, so let's get started. All right, so forecasting methods, we have four main types of forecasting methods. The first one is going to be the ensemble method. Now this is going to look at the degree of uncertainty. So when we're looking, there's many different models, and meteorologists will look at different models to figure out, what the model thinks will happen in the future. And if those models converge or agree with each other, then we have a pretty high degree of uncertainty. But if they don't agree with each other, that's when we're not as sure. We kind of like, our confidence is low in the models. And so that's where different models biases come in and different things like that happen. So that's where the ensemble forecasting comes in. The second one is going to be persistence, which is going to be where the future will be the same as the past. So, last year it was 70 degrees on August 10th. And the year before that, it was 71 degrees on August 10th. And the year before that, it was 72 degrees. We can be pretty confident that, it'll be like 71, 72 degrees. We can be confident, but it's not actually as accurate as you might think. So this persistence method is used a lot of the time by the big TV stations and the big, the non-national weather service, the non-government entities. They'll push these, they'll say that their forecast is, 30 days out or 2 months out. Models don't go out that far. So the only way that they can use, can look at 30 days out is the persistence method. So if one of my friends, was to call me and say, I'm getting married in a month, what does the forecast look like on that date? I could use a persistence method, and that's what I would use in that situation, but I'm actually going to tell them, I'm sorry, I can't really be accurate because it's too far out and the models don't go out that far. The analog method, this method is the one by far that meteorologists use the most. This is where, they use pattern recognition. There are certain patterns that emerge in certain areas of the country. And that's why you see meteorologists not moving around very much. They get to know the specific area that they're forecasting for, and they stay there because they get to know the patterns, what's happening, the things lead up to these events, stuff like that. And so they learn to recognize these patterns, and therefore they can figure out the biases in the models and which one to actually lean towards if they're not in agreement. And that, a lot of the time, is what will separate a really good meteorologist from, one that's new. And the last one is going to be a climatological forecast. This is one that's based on the climatology of a region. So I would never forecast that it was going to be, 25 degrees and snowy in San Jose. That pretty much would never really happen because climatologically it has never happened. So if I see a model shooting something like that out, then I'm going to definitely question that because the chances of that are pretty much zero. So that's where we can kind of use these climatological forecasts. Again, they're not as accurate as the analog method. That one is for sure, once you get to know the patterns of the area, it's a lot easier and a lot more accurate than the rest of them. All right, so the models. Now, what happens actually is models process many equations all at one time. It would be impossible for a human being to process the amount of computations that a computer actually does in order to give us our forecasts. And so our forecasts are actually reliant upon how fast computers are and how many equations they can actually solve at once. The more faster they are and the more equations that they can solve, then that actually increases our modeling and our forecasting and our accuracy. So what actually happens is, we take the data from the places. We already went over the data in the lecture 1 of this week. So, where we receive these data, we'll ingest it into the model. The model will run it through complex equations, and then it'll spit out the maps or the data or, what it thinks it's actually going to happen. Let's see. Now, forecasters do understand the biases of each model because each model is going to lean towards like different equations that meteorologists use more than others. And the other thing to keep in mind is that the longer the model goes out, the larger the resolution. There's very much a relationship between how far out the model goes and how big the resolution actually is. So the models that go out, 10 days into the future, they're going to be looking at a very large resolution. They're not going to pick up the individual thunderstorms. They're not going to pick up any type of tornadic activity. What they will look at, though, is the overall flow of the atmosphere and the overall flow over the United States. Is it coming from the north? Is it coming from the south? Is it coming from the west? Where are these air masses coming from and where are they going to? That's what these further out models, that's what a lot of meteorologists or most meteorologists will use that for. And then the closer it actually gets to the date, then that's where they're going to go into the models that actually get a finer resolution and they can pick up the individual thunderstorms and the smaller things, the mesoscale features. All right, so there's many models. I want to start off saying that there's more than just this for sure. And the other thing is I put nowcasting on here, although nowcasting is not a model. It's just I put it on this page because it is another range of forecasting that meteorologists use. So the long range model is going to be the GFS. That one goes out 8 to 10 days. Notice I say 10 days. It doesn't really, it goes out a little further than that, but I would definitely not be calling that accurate at that point. So this is going to be our longer range model, and understand, again, it is not very fine. It is more coarse. It's going to have a larger resolution. And the next one's going to be the NOM. The NOM is going to be more of a medium range, 3 to 8 days. You can go 1 day on the NOM, and you can actually do the 1 day on the GFS as well. But the thing is that's like its outside boundary. That's as far out as it can go. It can go, 8 days. And then we have what, I would consider what we call the HRR. This is a high resolution rapid refresh. So this one has a very high resolution to it. This is, 6 to 12 hours out. It's not even a day. But if we have a thunderstorm watch at the beginning of the day, then we can use the HRR to better understand the exact location and the exact timing of a storm that's coming through a region. Okay, so that's going to bring us to the nowcasting. This is actually done using satellite and radar, and that's when we actually are looking at what's currently happening right now. I use this a lot. Actually, I used it one time on the 4th of July. There was a storm coming through the region. I was at some function that had a band, and I was, hang on, the storm is going to be here in 15 minutes. You guys might want to start packing up your equipment because I didn't want it to get wet. So I could see on the radar, actually in the satellite, where that storm was, and I could, understand how fast it was going and infer when it was going to be at our location. So that's what nowcasting is. That is definitely used a lot with warnings, with watches, that kind of idea. And we're looking at the current conditions and kind of deciding where it's going to go and when it's actually going to hit. Okay, here's the group questions. As usual, please pause and see if you can answer these on your own. All right, so the process. The forecasting process doesn't start like today. If I'm going to look at today's weather and try to decide what's going to happen tomorrow, or if I'm going to try to decide what's going to happen tomorrow, I'm not going to start looking at tomorrow. I'm actually going to start looking at what happened yesterday, and then I'm going to look at today, and then I'm going to look at tomorrow. A lot of people will ask me, what's the forecast going to be? And I don't look, honestly, at the models every single day. And so without that knowledge of what's happening every single day, knowing what's leading up to that, then there's really no way for me to know what's going to happen in the future. It's at least harder for me to know what's going to happen in the future. You need to understand what's happened in the past and what's happening right now to be able to understand what's going to happen, tomorrow. And once you understand how we got here, where the flow is coming from, where is it coming from the north? Is it coming from the south? How much moisture, is there today in the air? Did it get rained out? Because if rain happens, then that moisture might go away, it might get rained out. And so it might not be there tomorrow. So we need to understand what's going on day to day before we can understand what's happening tomorrow. Okay, so the forecasting process is going to start large and high up in the atmosphere. And then it's going to go down, down, down in the atmosphere, and it's going to get finer and finer and finer. So we're starting looking at 200 to 300 millibars, which remember is way up there in the atmosphere. This is where the jet stream is. So we're going to start looking there, and then we're going to drill down and look closer to the surface. And the further down that we go to the surface, the more we're looking at smaller features. We're looking at more mesoscale type of items. So we kind of look at it as a funnel. First we'll look at it as hemispheric, then we'll look at synoptic, and then we'll look at mesoscale. But we're not going to spend as much time in this larger hemispheric product. We're not going to be looking for little fine-tuned little things. We're going to get the general idea of what's going on higher up, and we're going to spend the most time actually closer to the surface, where we're going to be looking more for fronts and things like that. Actually, more for thunderstorms, mesoscale type of ideas. Okay, so an idea of how we might use a 300 millibar chart, this is going to be like a map, is we're going to look at the jet stream. Where's the jet stream? How fast is that wind speed going? Where is the air coming from, and where is it going to? We can find it because these all have wind barbs on them, and we can see how fast the wind is blowing, and they color code it. This is taken from Twister data, but they color code it based upon the wind speed. So it's easy to spot out. It doesn't take us very long to find it. Okay, and then we're going to go down a little bit further, closer to the middle of the atmosphere. Now, we're looking at vorticity here, and we can tell that areas ahead of a vorticity max is where air is going to converge. When air converges, that's when it's going to rise, and it's going to possibly lead to precipitation. And then behind it, we're going to be looking at more divergence, and that's where air is going to be sinking, and we're going to be looking at more clear air. So we can kind of have a good idea from vorticity at a mid-level as to what's going on as far as convergence and divergence. And the last one I'm going to show you guys is going to be 700 millibars, which is a lot closer down to the surface. And this is where we're going to be looking for vertical motion, and we're also going to be looking for moisture. So is there moisture coming up from the Gulf into the plains? If that's happening, we're going to be looking at thunderstorms possibly, that kind of idea. Are we looking at, this looks like a little pressure system right here is closed. We can find these more fine-tuned things and see where, the moisture is. Okay, so I just want to point out to you that this is just the tip of the iceberg. There's a lot more that goes into forecasting, and the people that I know that do forecasting, they do it 24 hours a day, not 24 hours a day, I'm sorry, they do it 40 hours a week. That's their full-time job. They're very good at it. They look at it every day. They're constantly, keeping an eye on what's going on. They hand draw out the maps themselves. Us people, like, I don't forecast as much personally. I'm more on the research end. I might go and look at websites like Twister Data. I personally use the College of DuPage or COD. That's my favorite page, or Tropical Tidbits. If you Google these sites, you can get straight to them, and they can give you some great weather maps and some things that you can look at on your own if you're interested, because I know a lot of people that don't even have degrees that go storm chasing, look at, hurricanes, or they look at lots of different features in the atmosphere, and they go to these websites actually to find the weather maps and find the features. It's kind of fun to do sometimes. And this is going to be the end. Here's our group questions. So this is the end of the lecture for this week. I hope you guys are having a great week, and thank you for tuning in.